What is intelligence? That is the question that a lot of us have been asking ourselves as AI is showing up in more and more places. Some of us are using it now at our jobs. Some of us may be fearing that someday AI may make our jobs unavailable. Some of us only know AI on our phones and on our other devices. A lot of us have a lot of questions about what AI is and how it works. We wonder specifically, what exactly does AI know? How does AI know what it knows? And what does AI not know? These questions are critically important as they relate directly to our safety. They relate to the reliability of the products that we're using that have AI as part of them. They relate directly to our ability to do what we do as humans in our hobbies and in other pursuits. These are the kind of questions that we're going to be talking about right here on this show. This is the Breaking Math Podcast, and I am your host, Gabriel Hesch. This is our very first video version of this show. We currently have an audio version available on all podcast players. We now have a video shown on YouTube. It is also available on all podcast players, and it's airing first on the New Mexico Education Channel, Comcast 96. Quick shout out to you guys here. So I want to talk to you guys real quick about AI and machine learning and how it relates to math. There is a field of philosophy called epistemology, and I probably said that right. Go ahead and laugh at me. Epistemology. It's essentially the philosophy or the theory of knowledge and how we as humans know what we know and what assumptions our knowledge is based on. I would like to use some tools from philosophy and from epistemology, and also some good old bit-by-bit engineering and systems engineering to talk about how AI knows what it knows on this show. Real quick, for the last several months, I've picked up a book here. It's called A Brief History of Intelligence by Max S. Bennett. Actually, what this book does is it talks about brains and brain-like organelles all throughout nature. There are chapters that talk about brains in insects or in fish or in reptiles or in mammals and humans. And it talks about how they know what they know and essentially what hardware, between their ears is required for that. It is fabulous. So I suggest to any of our viewers or listeners, check out this book. You can go along. We also have a discussion happening on Slack at Breaking Math Podcast or Breaking Math Pod, as well as Discord or even our emails here. So, hey. Now, I have a very special guest today. My guest today is a creator who has worked with Khan Academy. He has worked with Pixar, with Disney. He has worked with Google. He runs a YouTube channel all about electrical engineering, computer science, and machine learning. And for the last 5 or so years, he's been making a series of documentary-style videos on machine learning. His name is Britt Cruz, and I'd like to introduce him. Britt Cruz, welcome to the show. How are you, sir?
Hi, Gabe. Thrilled to be here.
I am thrilled to have you here. So I'll just tell our audience again, since you've been in this field for at least the last 5 years, but really you've been doing your channel on computer science for the last 11 years, is that right? You have a lot to say on this topic. Can you real quick tell our audience a little bit about the history of your YouTube channel as well as your work at Khan Academy?
Sure. Actually, it's funny because it connects to memories. So when I think back, there's one strong memory, which is I was, I think maybe 20 or something, and left while I was in university or right after I finished. I went and did the classic working on the farm in the summer. Just went way up north Quebec. And again, just thinking back now as a parent, so busy with kids, having that sort of like weeks or months of total clarity, just literally digging holes and doing farm work, and then at night having no internet. Towards the end of that trip, I remember being like, all right, I've got to go back to school in the working world. I'm 20, what am I going to do? And in one notebook, I was like, well, what are you good at? List some things. The 2 things were I knew I was good, or good is what you're excited about video making in all forms. Also happen to be good at explaining things. And again, that's an interesting skill. I don't know if it's learned or innate. And so I just wrote like, and I also like some old TV shows like Connections, and I'm like, I bet if I did my own show, that would be good. And I wrote literally like I would do a show on cryptography, and then I would do information theory, computer science, physics, and one day I'd get to AI, and it's at the end of the book. And I know because it's one of those, I kept one or two books in my life and threw it in a box in the attic, and that one's in there. And actually climbed up and looked like over a decade later. I'm like, wow, that little insight on that farm was a thread that continues to this day.
You have a unique approach to computer science. I've heard traditionally a lot of folks don't like a degree program that focuses on here's all of your tools that you may or may not use. And I know that on your channel specifically, you don't start with the tools. You start with looking at the problem. Can you tell us a little bit about that?
Yeah. And so I put it in one line, which is you got to teach forwards, not backwards. And just as you're saying, it actually got like chills on like literally the torture of going through, let's call it a computer science program circa whatever, not this year. I don't know what it is this year, but since all of history, it was a lot of pain and struggle that didn't need to be there. And I think it's just kind of imposed on purpose to filter people out. That's an argument about universities, but in the context of computer science, teaching backwards is like trying to keep up with a bunch of modern things, a lot which won't even matter in the future. And then sometimes in a course being like, oh, and 200 years ago, so and so said that. And like, you're like, and I remember in school, there was like one or two moments where I'm like, what? There was something before we even had electricity that matters in computer science. I want to know more. And so the takeaway there is when I was thinking about how I would teach is kind of simple. I would just teach forwards. Teaching forwards means you have to unlearn what you know and go back to a blank slate. Oh man, that's important. And if you can go to a blank slate, which is any teacher can just naturally, a good teacher can just jump to blank slate and rebuild an explanation in that moment. That is what you have to do. And so that's how that's how I approached it.
Actually a former educator. I've been told at least I have an ability to explain things with stories and analogies, which is also a part of machine learning and how knowledge is stored distributively. We'll get to that here in a bit. So it's interesting. I want to mention my late co-host, Sophia Baca. She would love this conversation. She would love talking to you, and I miss her very much. We've done an episode already how Sophia passed away this last year, and part of why I want this show to go on is in honor of her and the way she'd like to do things. You know, she was very, very creative as well, but also my math tutor. So I was able to somehow code switch between creative ideas and analytical ideas. And how do you meet people who are good at doing both? Sophia was definitely one of those people and left their imprint on this show for sure. Amazing individual. So we are going to talk about some of Britt's previous videos that follow the same format as this book, where they break down knowledge in nature, in brains in nature, and then they get to the history.
Happy accident.
Yeah. Very cool. Very cool. Yeah. So I suppose I watched every one of your videos these last 3 weeks, and I tried to summarize them. And essentially, whenever I watch a good sermon or a good talk, they usually have like a big 5 takeaways or a big 3 takeaways. I had a big 3 takeaway from your videos, but then I made it a big 5 takeaways. 3 takeaways about layers of learning, and then 2 additional takeaways about what neural networks are and how they learn. Let me know how I do on the big takeaways, and let me know if you can elaborate on this. What I wrote is, from watching your videos, the 3 takeaways with learning are that in nature, you have examples of trial and error, which involves randomly trying something and then reinforcing it. That is used all throughout nature, including when toddlers learn or when bacteria is spreading or just about anywhere we look. There's another layer that's a little more complex. And that layer is what we know of as classical conditioning for those who have studied psychology. That's when, was it B.F. Skinner, I believe, who trained his dog to salivate whenever he rung a bell, because his dog began to associate that type of learning with a bell, you know, from he would always feed his dog whenever he rang the bell, and eventually just the bell itself would cause salivating in his dog. So that's associating a sense and an experience. And then the third form of learning is the most impressive. I think it's abstract imagining, and according to this book, it's how humans and mammals have the ability to imagine scenarios where you can play out a scenario in your head. You can imagine what happens if I walk over that pothole and I fall, but you don't actually do it. It's a step beyond associative learning, and I've heard it called internal modeling and simulation. Would you say that's a pretty good summary on the layers of learning?
Yeah, that's really good. And so I'll just compress your summary now,
Okay.
because which is that in the three layers, the first one is genetic learning, and the reward is life or death.
Yes.
And the way it manifests is our genes spill out into pre-wired connections that stay fixed our whole life. And that's why insects, you were saying earlier, yeah, he is on that alligator, and it's a he.
Oh yeah.
Is on autopilot in that context, but more specifically, when I start the video, it's that insect brain, fixed connections. That second layer is then we spill out into connections. Our DNA spills out into the ability for connections to change in life, so changeable connections. That's the key. And then what's neat about the third layer, it has nothing to do with connections changing. It's thought patterns in our brain are kind of at a higher level of abstraction making connections.
Right, nice, nice. And right now, I'd say if we're talking about neural networks, I've been trying to find the list of activities that neural networks can't yet do quite right. This is where there's some ambiguity with our current technology and what neural nets can do. Can you name some activities that right now a neural network can chat, whether it's chat, GPT, or anything else, cannot do?
Two quick points.
Sure.
Point one is be very careful when you hear someone say what neural networks can't do.
Yes.
99.94% they're wrong. And I'll give an example where I even found myself wrong, because there's a human instinct to draw a line way out and do the meta thing on the machines and be like, you'll never catch me up here.
Oh yeah.
And the one practical one I had is, and this is true, anytime it has a strongly learned pattern, something it's known very well, and in the human analogy, it would be some over habituated behavior, like looking at your phone. It's very hard to do the opposite. This is also known as it connects to the no free lunch theorem. You learn something, there's a cost.
Mm-hmm.
And so I was using, even in some talks, my favorite was, you can't play tic-tac-toe backwards. And I tried all the models and they all were failing. And I was like, I get to be up on my high horse, my human horse, and make fun of it. And everyone laughs in the crowd. And I remember in one talk, like, what is this, 4 months ago? It feels like 10 years. I'm like, once it does this and other similar examples, then I'll be kind of scared. And guess what? Now it can easily do that when we went to the GPT-4 model. And so A, be careful.
Okay.
B, where does it actually also, like, I'm still kind of sure it fails, is self-awareness. And so the practical thing there is runaway errors. Not being aware of errors as it is making them, and it leads to this explosion of errors. By the way, I want to talk about hallucinations because people got that wrong. But even see, when I say that, it's not self-aware of itself and it's going to have runaway errors. I already know of research where they're trying to, again, just add another layer of a neural network, in this case, a large language model, looking at itself, and you can get out of that error. So I'm trying to partake that it's not a list of what it can do and not do. It's a very blurry, everyone's walking in the dark with their hands out right now.
Oh, that's so philosophical, that's so existential, and that's the world that we're in right now, isn't it? So in this outline, I want to real quick shift to going over your first video. You have some fabulous diagrams here where you have some diagrams of what's happening in basic brains. Then we have examples. Some of my favorite examples from your first video is there's things like bacteria that can only sense smell. It can only either go in a random direction or a fixed direction. We talk about Venus flytraps as well as, oh, I didn't get the name of the leaf. There's a leaf that curls up, but it can learn to not curl up. Simple diagram, very simple diagram. There's a blue circle with goals, then it has an action and a sense. Britt, would you mind explaining the simplicity of this diagram?
In the middle there, I know we might have audio, is just a circle representing, just call it an entity, which has some goal. And so the goal, again, just to be clear, could be survival. It could be something else.
Yeah.
It could be a sub-goal of that. And it can sense things, perceptions, arrow going in, and it can act sometimes by changing its body in some way.
Okay.
And so what I'm done here is actually looped the line. So it goes, the action loops around and becomes its part of its sense. And that's a simple but important idea.
Okay.
I'm actually looking at it now. It's so simple. I lose sight of why I drew it.
Awesome. So what I love that is I love the simplicity because the question in your videos is what is the simplest brain out there? And we were talking, and I forget if we were talking on Twitter or X, whatever it is, but we were talking about how when sense folds in on itself into action, and if something is able to like smell something and then choose an action from that, that is essentially the most basic type of a brain. It's something that responds to the environment. One example I've heard brought up is thermostat. You could look at a thermostat as a brain or a coil, and in response to hot or cold, it expands or contracts. So that's one example, but I like your examples better. You had we said earlier, the first one was imagine a bacterium, a single cell organism that only senses smell. And this baffles me because at a philosophical level, what does it mean to smell something? It's a very hard sensation, but is it from an evolutionary standpoint, is that the first sense that ever evolved to your knowledge?
Yes, well, it specifically smell. I just want to say that all senses are the same, and so they're just energy levels that hit this sensory neuron. And I want to say senses, but I not 100% sure. It felt right.
Now, real quick, I want to mention something very important here. This here, without any more complexity, this very, very simple brain, this one diagram, one loop, it's a fixed action. You use the word fixed action in your video. That means it can't change. Something like, and I think the example used is a Venus flytrap or any kind of a trap. If you stimulate the sense on a Venus flytrap, it closes. And that's just about it. It'll always close, and it's always the exact same thing. There's a slight evolution here when, and I think the example you gave is, let's say you've got a mutation and you have some more connections pop up inside that brain, and you've got some more wiring. And there's a diagram as well. And looking at this diagram, I'm thinking about a very, very early neural network. You may have a different diagram in your videos, but I was thinking of, those red lines on the inside. Basically, like if you have a neural network, there's a bunch of possible pathways, and not every sense will have the same result, and it can change over time.
So it's good to repeat that, like, what's machine learning really doing? It's how to act. How to act is given an input, what's the output? I just like to repeat that because things can get confusing really quick to anyone new to this. Yeah. How to act in, out. And so I was looking for examples where the connection between input and output can change in life, which is a huge, huge advantage. And the way it first changes is not through new connections growing or anything. It's actually just turning down a connection, inhibiting a connection gradually. And this is what's so cool where habituation comes from. It's just not doing something as much. That's kind of like this baby step in life learning. And this is a leaf that, after a while realizes that getting hit by water is not a bad thing.
I'd like to talk a little bit about the early research into machine learning and some of the clumsy early models of a neural network, ones where you had to like manually change each dial. I was hoping that you could give us just a quick little preview of early research in the clumsy early models.
I'm glad you brought up a dial. So the original dream was, let's make a mesh of wires with just neurons and wires connected. And a neuron is like in electrical terms, it's a transistor. If it gets enough energy, it turns on. So you need something to be your neuron, and that thing basically you can use a transistor. And the only other thing you need is connections. But we need to be able to change connections. And so this is why I use, and I made this up. I don't think they didn't use this, but I used a dimmer switch to hint at this idea of a dimmer switch is a variable resistor, which allows you to change the strength of that connection electrically. That's all you need. Then you have to give it, again, machine learning, all of learning, input, output, how to act. And so the first experiment was so great. Rosenblatt's was just like he used like 50 neurons all connected together, thousands of wires, but he would either draw on like a light, bright style screen, very low resolution, a circle or a square, and then have the machine learn circle versus square. And how do you learn? Well, you got to give it some experience. So he'd draw a circle, put it on an initially random mesh of connections. And that I need to amplify super clear because there's not much to machine learning if you got the core right. Random mesh of wires, well, it doesn't work at all at first. What's not work mean? Well, the output is forced to be one of two things, and we can call it circle or square. And in this case, that's what he wanted to do. And so when you put but it does nothing at first. So you put a circle in this machine, and what happens with the two light bulbs at the end? The machine doesn't know anything. They're both kind of lit up just kind of randomly. And so it has to learn. What's learning? Well, in this case, the human kind of cheats a bit where we show it a square. It does some random thing that doesn't work. Then one by one, we go through and wiggle each dimmer switch. And sometimes going one way will help, meaning, oh, I human, am going to let's call the top light bulb a square and the bottom light bulb a circle. Anytime I put a square in and I do a wiggle, when the right light bulb gets brighter, I'm going to keep that wiggle. If it doesn't help, I'm going to go the other way. And you literally just do that through all the neurons. Keep doing that. And you hit a point where you put circles and squares in this network and it doesn't need you to do any more wiggling. That's the time that it has generalized, which means it'll work on what it was trained on. But most importantly, it will work on new circles and squares you draw, different people with different handwriting, different pixels, basically.
Yeah,
that is like what we're still doing today. Nothing really has changed.
Interesting. One of my questions as I was watching your videos is, so theoretically, you could build a neural network out of like anything, a bunch of breadboard pieces. You could build manual switches and like have it out on a table. And yes, it would be very clumsy to go there and manually change everything. And that's one of the reasons why machine learning didn't really take off until the hardware caught up. And I think 2009, when graphics cards became available, I think that was a major turning point in artificial neural networks. Is that right?
That's right, because it can multiply a big chunk of numbers instead of one at a time.
Nice.
It wasn't anything special beyond a happy accident.
Very cool. Very cool.
Yeah.
There's two videos that we're going to watch from your series here that'll be up here in a second. One of them is on deep learning. It involves the paper folding analogy. And the other one is from the exact same video shortly after. It's on probing neural network layers, where if you've got a neural net that is trained on recognizing images, what happens when you peel back every single layer and you look at what's built up throughout. So I think without further ado, let's go ahead and do it.
Organic brains use layers of neuron activations to process their inputs. The importance of depth, or many layers, is the least understood aspect of neural networks. So let's pause and consider a simple analogy to understand why multi-layered networks are better at partitioning the perception space than a single-layer network. Imagine this is our perception space, and we have two kinds of input data types. Each neuron we add in the first layer acts like a fold in this space. With two neurons, we can make two folds like this. And we could keep going, folding and unfolding the paper to carve out regions to separate these points. This will take 6 separate folds. This allows us to then group regions containing the same type of points using a final neuron which activates if any of those regions are active. But now consider what happens if we layer our folds. That is, we don't unfold after each fold. So let's do the first fold again, then the second, then the third fold across that layer like this. That ends up carving the space in the exact same way, using 3 folds instead of 6. And if we were to continue this process with a 4th fold, it results in 16 regions. Practically, this means that neurons deep in a network are not simple linear partitions, but are instead activated by a complex pattern of linear partitions.
Tell us a little bit about that video and just put it into more layman's terms, even though it's already in layman's terms.
When we're talking about neurons, they just have inputs and an output. One way when you want to think about it mathematically, and let's just use the example of a temperature, we're trying to make a neural network that can let's go to a thermostat, that you just set what you want your temperature, your dividing line. A neuron really in math world where you're just plotting temperature on a line, like 60 degrees versus 62. What is a neuron? It's actually just a divider. Think of it as a point on that line. Or in 2D space, if you have a couple variables, like a pressure sensor also attached, it's a line, it's a partition. It's just dividing sets of points, which are senses. A sense is just, in a mathematical term, a point on a line or a point on a plane, into two categories, and that's how it knows one thing or is another or versus another, that essential difference that we build everything on. So that's all a neuron is. And when you put lots of neurons together, you get lots of partitions. And what do you do with lots of partitions? Well, you can define complicated shapes. And that allows you to capture more complex concepts. And so this is why there's a resultant neural in AI where you only need one layer really to do anything. A neural network with like an infinitely wide layer of neurons and all the connections going in and out. In theory, it can do everything, but in practice, it doesn't work because you can't make something big enough in practice to do problems. You need too many partitions, too many neurons. And the trick they found was if you layer neurons, so instead of trying to do like 100 million neuron wide network, you just do like 10, and then another layer connected to 10, and another layer connected to 10. Those actually multiply together, leading to the same amount of partitions with very few neurons. And so this sounds so complicated. So if you're confused, it makes sense. Yeah. So I needed a physical analogy, and my physical analogy is you fold a piece of paper, that fold is a neuron. And so if you try to fold and unfold a paper to do all your folds, you have to do one fold per fold. But if you fold and then fold again and do that classic thing where if you fold a piece of paper like 12 times, it goes to the moon. When you unfold your paper, every fold you end up with is like a neuron. So with just a few folds, you can get many folds.
So that's a very cool one. And then we got this next video. And
took a neural network which was trained on real images, such as ImageNet, and then probed individual neurons to find out what activated them or what turned them on. We probe neurons in the first layer of the network. We find they are detecting these patterns, which are looking for edges and points. Then they move to the next layer deeper into the network and probe those neurons to see what activates them. What they found was the next layers are activated by different kinds of textures. And deeper into the network, these textures get more specific. And as you move deeper into the network, the textures get more complex. And the deepest layers contain individual neurons that are activated by entire objects, such as dogs, wheels, houses, or trees. These complex activation patterns are possible due to the layered structure of the network. And so if we cut open a neural network, we'll find the deep layers contain representations of a perception based on what level of different things or patterns they contain, which is defined by how active those specific neurons are.
Very cool. Yeah, I think that was a fabulous video. Where did you find that example, if I may ask?
So that visualization is probably from the work of Chris Olah. Look up him. They've done, and Distill have done a lot of great work visualizing the innards of neural networks.
Nice. I want to talk about some of our favorite examples of AI that we've used and why, as well as some of the examples that are brought up in your videos that we haven't discussed yet. Do you have any favorite examples of AI in any use in industry or entertainment or elsewhere?
What I find most impressive is not any specific use, but the pattern of what's happening. And I just put it simply, it can handle such messy input, unstructured, messy, noisy input, that all we need to do now to interface with computers is utterances and gestures, or one or the other. Just with the most simple utterances, simple hand waving, the machine has everything it needs to do what it needs to do. And so whether that means there's new graphic design software where I just kind of go, make an ocean. And even when I say it, the sound's all fuzzy and maybe I pronounce it wrong. And I'm like, and make the wave look like this. And I just whoosh my arm around. It's going to output a beautiful painting. And I remember as soon as this was possible, I made some for 1 year for holiday gifts. And so you just see that again and again and again. The simple utterances, look at ChatGPT, but also just simple gestures is all you need to do to interface with the machine. And I think that's just, we're still getting our heads around that.
That's amazing. I kind of think of like when a husband and a wife know each other after many, many years, and you know just from their facial expressions how they feel about a certain situation, you know? Now, there's a part at the very, very end of our outline here where we're talking about your talk at Google, and you had mentioned some really impressive AIs. I think one of them was it a student who you saw build a social media platform just with AI in a very, very short time. Can you talk about that a little bit?
Yeah, so this is an example of a woman who kind of had no coding experience. And you'll see this pattern everywhere now. That's why this year is exciting. And that said, oh, I want to kind of make a Duolingo meets Netflix for learning languages. And how the app works isn't so much important. What's important is she was able to prototype it in 3 days and be walking around on the street handing her app to somebody. And anyone who's tried to build anything knows going from idea to someone holding it in their phone testing it sometimes never happens, or takes years, or takes months. It doesn't take 3 days with some simple utterances. And so she was able to do that, and that's where we live now. So everything's being kind of restructured around that truth.
That is amazing. Okay, so you said Netflix meets Duolingo. So something, I mean, do you have more details on? I'm curious about the app now, actually. So
I think it was, I know, right? So traditionally you just get subtitles. This game, I'll just put it, gamified the subtitles. So imagine no one's even thought of that, which is, I don't have the app, but just imagine some words are different colors, or maybe questions pop up on top of it. I don't know, but it was this idea of gamifying subtitles, like how brilliantly Duolingo gamifies things.
yeah, yeah. Oh, fascinating, fascinating. Yeah, actually.
And so how would you build that? You'd need multiple engineers, and you'd need you need a couple engineers or one brilliant one, and a lot of time, but she didn't.
Okay, that is amazing. I wanted to bring up this section about AIs specifically. The example I previously mentioned is the AI called Bakery Scan that was built for a Japanese bakery that is now used, or a model of it is now used to identify precancerous screens, or sorry, tumors in an MRI screen. What fascinated me about this AI is, in this Japanese bakery, there were two AIs that were created. One of them was done through reinforcement learning over a period of 5 years by a team of programmers that really understood the bakery, and another one was done entirely unsupervised through deep learning. For the original purpose, which was identifying baked goods in a bakery, they were about on par. They were about equal. But then there's a critical task where one of them outperformed the other. The critical task is learning new baked goods. And what they found, and I've got my citations here, what they found is that the supervised learning model learned at multiple orders of magnitude faster than the deep learning model. So that to me was fascinating. I didn't see that coming. I literally thought the deep learning model would learn it much faster, but that's not the case. So in that use case itself, I'm dying to know, why is it that the model trained by a human who knew the bakery inside and out, and he knew what to look for, why is it able to learn new things faster than the deep learning model? I don't have an answer for that, but that's the kind of questions that are relevant right now.
Yeah, there's one potential confusion there, which is both are deep learning, meaning they're using layers of neurons, but they're using two different approaches, which is supervised and unsupervised. Yeah. So that's the key difference.
Okay.
And what's neat about supervised, what it really means is the human's providing the reward every time. So you give it bread and say what it is. Give it bread, say what it is. Do counter examples on both sides. Versus unsupervised, where you're letting it learn that itself. And so in many cases, and still to this day, I call this narrow siloed AI. When you use again, it is deep learning, but it's humans providing the labels and the examples over and over. You get very high performing systems, but they're not generalizable, so they can't do other things. And that's why there's a cost benefit there when you go to more general systems that may fail narrow. But yeah, I hope that was helpful. It
definitely was. I also thought that, like, in terms of acquiring knowledge for a specific task, in this case, the task is a human-centric task. Humans are the ones that make the baked goods. Humans are the ones that eat them and that evaluate what's good or what's not good for human purposes. Well, frankly speaking, we have insider knowledge on what makes something good for us. So that also is very helpful for something that learns new tasks, and that is yeah. So I think that's optimistic that humans will be in the loop for a lot of tasks in the future. We won't be obsolete quite so soon. At least that's my assumption. I don't know if you'd argue on that one.
I don't want to argue. I want to throw in one fun example I didn't tell you about. And
Okay.
this, again, is this a failure mode or a feature? So on a different cancer detection test, they had an AI looking at cells and it could tell whether or not it was cancer. They gave it two batches of data, had it learn, and it did it better than a human. And then, so, hey, you could stop there and say, wow, it's brilliant. They looked into why, and again, it learned how to act. Act means say cancer or no cancer with what we thought was a hack, which is it noticed that in all the cancer images in the data set, there was a ruler in the image. And in all the non-cancer, there wasn't a ruler in the image. And so what did it learn? It just learned immediately, you see ruler, it's cancer. And so that's a fun example of like, it'll learn what it needs to learn to do it. So if you take that ruler out, well, guess what? It's going to notice other subtle differences and it will work. But I love that ruler example because is that a bug or a feature? I would say it's the feature.
This next section, are there any interesting complete failures of AI that you're interested in talking about?
Maybe just that when I mentioned earlier, I want to say it's lack of awareness of itself, but I don't know how strong I feel about it right now. So I'll just say the current kind of boundary of what it can't seem to do is on the one hand, people say it doesn't have a world model. It doesn't really understand the physical world because it didn't grow up crawling around and getting dirty. But so that's the boundary. Like it doesn't really, with language, it can sound intelligent. But their argument still, this is not my argument, is when ChatGPT says water, it hasn't felt water. Fine. But that is currently the edge of research right now, and it's amazing. I sent you one video of just teaching a simple robot to walk in the grass. We went from it taking like impossible to 20 weeks to 2 hours, and this thing's babbling around learning to walk. And so
That
the
video was
physical
incredible,
world
by the
seems
way.
to be the failure. Yeah, right?
Yeah. One of the questions that I've been emailing you a lot about lately is I'm trying to think about digital learning through a neural network versus a biological brain. You know, because like we can learn to play chess, and you know, I imagine there's some rewiring. I think there's rewiring. I'm not sure how much actual physical rewiring is happening in our brain, but you know, I think about power consumption of our brain versus a machine, and what are the limitations, and what, you know, a machine can learn in 2 hours, but really we're fighting against the fact that our rewiring is not just a digital thing. It's actually a physical thing, so it's more like a muscle. I just don't, this is where my neuroscience lacks. I don't know if you know a lot about the actual human process of learning and pruning of neurons. How is that different than machines?
I'll go with two examples on this power consumption thing, which is, of course, evolution has found a million awesome hacks. So one is that neural networks in the brain aren't on or off all the time. They're sending spikes at different rates. So fast is on and slower is off, and they can be continuous. And so on the one hand, that's smart just because it's only sending bits of energy once in a while for an on, not staying on. Duh. But also it gives it an ability to send continuous signals, which can process much more information. So it's always, can you do more with less? And another one, what we call in machine learning, is pruning. As we know with the human brain, you could like go in there and often just snip random neurons and nothing's going to happen. It's only when you damage a big chunk, like billions of neurons, even then sometimes nothing happens. It's incredible. Yeah. You have to like torch your brain and pull chunks out for it to fail, unless you happen to hit this perfect neuron that's critical. So pruning in AI, what we do in machine learning is you just like randomly, just instead of having a fully connected network where everything's connected to everything, you just randomly start deleting stuff until it stops working. And this is called a sparse network. You can get by with a very sparse network. And so nature is doing those things and many more, and things we don't understand, but it's just doing more with less power. It's really cool.
Yeah, that's incredible. There's so many things on this outline that sadly we didn't get to that I know we are running out here on time. I want to do one more video There's one video that talks about art in language, and it involves the field of linguistics, which is a human activity. I'm hoping to play this video real quick. That's the one.
I think people realize that there is no difference between art and language. If you start with the earliest cave paintings, they do the same thing words do. They serve as symbols representing a concept. Just like we can use the word ox to talk about the concept of an ox, this picture also communicates the idea of an ox. And it's precisely because of the blurred boundary between art and language that writing systems developed in the first place. Eventually, people realized that an ox could represent more than just an ox. So they start using stylized ox heads to represent sounds, and then that evolved into the letter A. And the same thing happened when the Impressionists and the Post-Impressionists realized they didn't have to paint reality as it is, but that they could abstract the representations of it. Then slowly but surely, painters like Picasso realized they could push their representations further and further from reality. Which is why I hate it when people look at a painting like Elaine de Kooning's abstraction of a standing bull and say, oh, my child could draw that. This is actually an anarchic critique of the relationship between symbols and meaning. And all poetry does the same thing. This description of a pair of oxen doesn't describe the oxen as they exist in reality, but it serves as a representation that each of us will visualize slightly differently. At its core, art and language do the same thing. They're inextricable, desperate attempts to capture pieces of our conscious experience, which is so beautiful. I don't think...
Okay, awesome. Thank you. Watching that video and watching all of your videos, I had this whole idea about how an image generator, something like Midjourney or DALL-E or any of those things, they've been trained on these images, and their knowledge of any concept, like a cat or a dog, exists distributively in their head. But just like humans, at some point had the ability or the desire or the need to draw a minimalist depiction of these images in their head, and they were recognized, there's this key data that's captured in a drawing of a cat that multiple people can recognize. So I'm curious how soon it is until Midjourney or DALL-E is able to create minimalist pictures and then further abstract them into their own alphabet. I'd love to write a paper on an artificial alphabet created entirely by an image generation network. What do you think about that idea?
Yeah, it's a fun area to think about, and I love information theory because communication at its core is how one mind influences another, and how efficiently can you do that? And so, of course, art, language, and art are the same. But if I wanted to tell you something and I'm going to draw a whole picture of it, that's going to take so much time. And so the more compressed you can get that representation, the better. And yeah, I've seen a bit of research on neural networks talking to each other in their own code or their own language, and super fruitful area to think about, especially when we want to download our current mental states and recall them later.
Before we wrap it up, is there anything else that you would like to talk about? Anything you'd like to plug?
Sure. This was a lot of fun. The outside of YouTube, the other thing I do is I have a company that created a product called Story Experiential. That's experiential with an X, with my two partners, Tony and Elise. And it's a kind of online peer-to-peer learning model I'm really excited about. Thinking about what won't AI do is facilitate human-to-human creation. It won't get rid of the humans. And so I'm really interested in this peer-to-peer learning model online. And so I want to build other experientials in other domains as well. So check out Story Experiential.
All right. Well, Britt, thank you so much for coming on the show. I've had a blast. This has been a journey, both with preparing this outline, but also just preparing the body of knowledge that is artificial intelligence and where we're at. One of the biggest challenges was to do this in a way that breaks it down for an audience that may not be familiar with it. I tried very hard to do that. But again, we will continue this conversation. If you're on Slack, I'll put all the links in the YouTube video as well as in the podcast link. You can continue this conversation through email or through Twitter or X or through Slack or Discord. All that information will be there. Also, everything we mentioned from the textbook by the Professor Steve, or who goes by Eigen Steve on Twitter, and everything else. So I think that's it. Thanks again, Britt. It's been a pleasure. I hope to continue our conversations as time goes on.
Thank you, Gabe. It was a lot of fun.
Yes, sir. Sure was. All right. Take care. Till next time.